let's continue. And we continue by introducing a technical part, one of the most relevant technical parts of this course, which is water resources assessment. The screen is just for me, but in order to remind you what I'm talking about, but it's not necessary that you read in the screen for now. So, we talked about possibilities for solving water resources management problem, possible solutions. And we talked about reducing the impact of the streams in reverse order. We talked about demand control and regulation. We talked about increasing water supply. These are possible solutions. At the basis of any design activity related to designing this solution, there is water resources assessment. Water resources assessment addresses a very simple question: how much water is available? And it seems that it's a trivial question. It's not. So please keep this in mind, because it's an important concept. It's not a trivial step, it's not a trivial task to assess what is the amount of water resources that we can use. Even if we identified our water source, like a river, like a lake, like groundwater resources, a key step is to identify how much water we can take from the identified source without compromising the source itself, without running the risk of adopting an unsustainable solution. What may happen, for instance, if you take, and this is what happened actually in most of the developed countries, if you take too much water from a river, it means that you release only a limited flow downstream, and you may compromise the ecosystem downstream. If you compromise the ecosystem, water downstream becomes very polluted for a very simple reason. Think about a release of contaminants in the river. The release of contaminants can be due to a sewer system, and this is what normally happens. Even if water is treated, even if wastewater is treated, you release in a final receptor, which typically is a surface water body, you release some water that is not clean water. And if this water that is not clean gets diluted, then it's not a problem. But if it doesn't get diluted, because in the river there is a very reduced water flow, then it becomes a problem. Keep in mind that any ecosystem has some capability to be resilient, to absorb shocks. But if you compromise the quality of the ecosystem by, for instance, reducing the river flow, resilience is reduced. So this is one possible problem. A second possible problem is that you take water from underground and you take too much of it, which means that the underground water body doesn't have enough time to recover, to get replenished, because groundwater flow is very slow. So we have to assess whether the water withdrawal from underground is sustainable. It means, sustainability in this case means capability of the water body to get replenished. This is another possible impact that is maybe extremely dangerous. Other impacts related to overexploiting water resources are treated by the literature, and they range from, for instance, if you take water from a river, it may happen that downstream there is a limited recharge of groundwater resources, again, unsustainability. If you take water from a lake, it may happen that you reduce the water level in the lake, and then you compromise the natural equilibrium of the lake to mix, for instance, water in different layers of the lake. We don't study limnology. It's an extremely interesting discipline. Limnology is the science that studies the lake ecosystems. It's an extremely interesting discipline because, for instance, I learned that there is a continuous seasonal mix of water in lakes. During winter during summer they get stratified. There is no mixing between deep water and surface water in a lake. When you change the season, there is some exchange of water, mixing. So if the water level is reduced, this mixing capability may be reduced as well, compromised, and therefore this is another possible impact. So there are several issues that may arise. And therefore it's compelling that we assess what is sustainable, how much water we can take without compromising sustainability. This is water resources assessment. It's a very technical issue. It requires making measurements, monitoring. It requires monitoring. Water resources assessment is strictly related to monitoring water resources. And let me say that in order to, when we have to perform an assessment of water resources, we have to refer to a system. Typically, it's a water distribution system. It's a water resources system. The system may be an aqueduct, the system may be a groundwater body, the system may be a river. We have to identify what is the subject of our study. This is trivial, I mean. If you want to take water from a river, okay, that's fine. You have to identify the subject. You have to study the river flow, the river regime. If we want to study the distribution of water in an aqueduct, our system is the aqueduct. So we take for granted the water sources, we take for granted the demand, and the question is how to distribute water in the optimal way. So you have to identify a system. What is a system? And in particular, it's a dynamical system. What is a dynamical system? And we can define in water resources assessment, there is the definition here. Dynamical system may be defined as a particle or an ensemble of particles. In our case, they are fluid particles whose state varies over time. Okay, that's fine. I mean, you define the dynamical system as a particle, a body, or an ensemble of bodies. As I said, typically in our case, it's fluid, so particle of fluids. They change their state over time. This is the essence of dynamical. And in changing the state, the system obeys differential equations involving time derivatives. So you have differential equations establishing, dictating how the system evolves. At this point, I want to make a note. First of all, why a differential equation? Because sometimes the system is heterogeneous, which means that, and it's heterogeneous and unsteady, which means that everything changes in space and time. And therefore, we cannot refer to a finite element. We have to refer to an elementary part of the system. So we cannot refer to like a cubic meter of water, because in this cubic meter, water changes its velocity, for instance, and changes in time. We have to refer to an elementary fluid particle, for which we assume that the volume and the mass are very tiny, infinitesimal, in order to make reference to something that can be assumed as homogeneous. So the velocity is just one velocity vector for the fluid particle, because the fluid particle is very tiny. Otherwise, if I consider a volume that is bigger, I may have different velocity vectors. Of course, I want to study how this body moves, how this water moves. And this is why I am referring to the velocity vector. Now, when I have these changes and then I have to refer to the micro scale, then I need to use differential equations. But the positive issue, the positive note, is that you don't have to be concerned. Differential equations are just normal equations. But instead of describing a variable in an explicit way, they describe the increments of the variable. This is just the only difference between an equation and a differential equation. I am interested in a variable. Let's say that it's the velocity, like the module of the velocity vector. An equation gives to me the value of the velocity. A differential equation describes the increments of the velocity. And these increments can be in space or time. That's it, but it's not more difficult. The only complication is that, so let me use this small piece of blackboard, or let me use some more than a small piece. So as I said, let's suppose that we have to describe this velocity of a fluid particle. Okay, so I have this fluid particle, which is part of a bigger domain. Okay, this is water, for instance. Think about water in a river. And I study this fluid particle, okay? And I am interested in the velocity. An equation is something that says, v is equal to a function of x, y, z, t. 3 coordinates in space, 1 coordinate in time. I'm taking a very general approach. Space, in general, you know, it's 3 coordinates. Okay, this is an equation. A differential equation is simply written may be written in this way. Okay, it's partial derivative of v with respect to time. So, let me say something about the partial derivative. So what is the derivative? It's an increment. Okay, it's an increment of v. But, as I said, this increment can be in space or time. So if I study the increment in time, I need to call it the time derivative. And given that v varies depending not only on time, but also depending on 3 spatial coordinates, I have to call it a partial derivative. So you see that the concept is very simple. The derivative is an increment. In this case, it's a derivative over time. It's an increment over time. And given that v doesn't vary only along time, but also in space, I call it partial derivative. And I insist on that because we are engineers, basically, maybe not all of you, but I think you all are studying engineering, so you are going to be engineers. And as engineer, we have a good knowledge of mathematics, but not an excellent knowledge of mathematics. And sometimes, when, at least me, when I have to deal with some complex concept in mathematics, I get a bit concerned, like, this is too difficult for me. And this makes your capability to solve tasks reduced. So I want to make clear that these are very simple concepts. And I'm dedicating some time because I think it's worth doing it. So, to clarify what is the meaning of concepts that you learned in math, what is the technical meaning? Because if you understand the technical meaning, you understand also the concept. So you understand the partial derivative only if you get the connection with your problem. If you don't get this connection as an engineer, you don't understand what is the usefulness of a partial derivative. So this is why I'm spending some time. So, partial derivative over time is a function of, again, x, y, z, t. And to be rigorous, I have to make clear here, and I should have made clear also here, the dependence of v on the coordinates. Okay, sorry if it's not very, okay, and even in this case, x, y, z, t. To be very rigorous. Of course, if we want to write in a simple way, we can drop it. It's an implicit assumption that we know it. And therefore, at the end of the story, but I need to get the value of v. So what I have to do, I have to sum these increments to get the value of v, because from a technical point of view as an engineer, the increment of v doesn't tell anything to me, or almost anything, let's say. At the end of the story, I need to get the value of v, and therefore I have to sum these increments. And when I sum these increments, I am doing nothing else than an integral sum of increments. This is an integral. Integral, it's another word that is concerning for an engineer. Shouldn't be, because it's just a summation. It's just a sum. The integral is a sum of elementary increments, nothing else. But there is to say that if you want to get the value of v, you sum the increments, but you need to know some more, the starting value of v. Because if you know the delta v's, and you want to compute v, you need to know an initial point. Because v is equal to v0, starting value, plus delta v's. This starting point is given by the initial and boundary condition. So other two terms that sometimes, oh my god, integral, initial and boundary condition, partial derivatives. Initial and boundary condition are starting point. And we say initial condition when we refer to the starting point in time, boundary condition when we refer to the starting point in space. I say again, because I want to make sure that you understood. You need a starting point for v, a starting value. But this starting value may refer to time, so may refer to time 0, or this starting value may refer to space. If it refers to space, it's boundary condition. It's called boundary condition, the starting point in space. If we are talking about the starting value in time, we call it the initial condition. So, what is the moral of the story? This body of water is heterogeneous. Velocity is varying over this volume. So I need to refer to elementary particles if I want to study their velocity, because I can assume that in this small, tiny particle, velocity is constant. And therefore, I write for v differential equations that apply in this body of water. V varies over space, inside the volume, but it varies also in time. It means that even if I refer to a fixed point of this volume, velocity varies in time. So I need to write partial derivatives. And then, if I want to know a velocity value for all of this volume, I need to compute an integral. Of course, be careful, when you compute an integral, when you integrate over a domain, in this case over a space domain, the velocity value that you obtain is the average for this volume. Integration means computing an average along the coordinate of integration. Okay, now, your question may be, but is it so complicated? Not necessarily. Meaning that this is a physically based approach. So, this kind of approach means that you understand the laws that govern your system, like conservation of mass, conservation of energy. This is a classical approach in fluid mechanics. Some of you already took some exams in fluid mechanics, and you remember conservation of momentum, of energy, mass. These are physical laws governing the system. And therefore our reasoning is, okay, given that I know the physical law governing the system, let's take advantage of it. So let me use these physical laws to describe how the system evolves. I'm saying physical laws, but they may be thermodynamical laws, chemical laws, ecological laws, biological laws. Usually when we talk about water, movement of water, and not water quality, let me put aside water quality just for a second. If I talk about movement of water, it's the laws of physics. So this is why very often I say physically based. But if we talk about water quality, then some chemistry comes into play. And then the model could be not named physically based, but some more. Okay? So, but the concept that I want to fix in your mind is that this kind of approach starts from the knowledge of what's going on, theoretical knowledge, so you understand the process, and then you write these equations. Let me give some examples. When you study the motion of water into a pipe, what you write is to impose conservation of energy, conservation of mass, and then you describe the movement of water. When you describe movement of water in a river, same thing. You impose conservation of momentum. Momentum in Italian is quantità di moto, for those of you that are from Italy. And you impose conservation of mass, and that's fine. Climate change, when they build climate models, they start from thermodynamical equations of the atmosphere. They write this equation in differential form and they integrate over the whole domain of the atmosphere. These are excellent examples. And indeed, it's a bit complicated. There is some math involved, there is some analytics. Keep in mind always the presence of uncertainty. Even if you write differential equation, you always have uncertainty in there. And as an engineer, you must care about uncertainty. When you use any kind of design approach, a lamp should turn on in your mind, which is the uncertainty lamp, and the question should come to your mind like, how much uncertainty is here? What is uncertainty here? Okay, and then we will discuss about it. But there is uncertainty. This is a distinguishing feature of water resources management, uncertainty. You cannot avoid it. Okay, but there is an alternative option, because as I said, this is a bit complicated. So the alternative option is to use empirical equations. And you know that in engineering we use a lot of empirical equations. Empirical equations are derived in a very simple way. They may forget, if they want, about the physics, about the underlying theory. The empirical equation look at the process, we observe the process, and then we derive an equation in some way describing what's going on. So we identify our design variables, the velocity, but we forget about conservation of mass, conservation of energy. We go over a river and measure the velocity for some time, and then at the end of the story we say, here the average velocity is 10. This is an empirical approach. And it's called inductive approach. When you start from the theory, we call it deductive approach. When we start from observation and we don't care about the theory, or we care about the theory only marginally, only partially, we say that the approach is inductive. Inductive because it is induced by the observations. And keep in mind this difference. Empirical models, largely used in engineering, typically inductive. Process-based model. Process means physically based, chemically based, thermodynamically based. They start from the theory. They are called deductive. In water resources assessment, very often we use inductive approaches. So the problem is You may say, oh, well, I'm lucky, this is is less complicated. Actually, it's less complicated until you go over the field to take measures, and then you realize that it's very complicated. It's complicated from an operational point of view, but still, it's a complication. Think about, for instance, we are interested in floods, not in this subject, but we are very interested in floods. And if you try to go over a bridge and measure the velocity of a river during a flood, you understand that it's extremely risky. So you don't find anybody that is willing to go in there, unless it's a researcher that is a bit crazy, you know. And so it's a bit tricky. So this is what I wanted to make clear. And let me see if but I don't want, let me close it for now. I don't want to be, I want to keep the blackboard. Let me see if I forgot something. Yeah, I think I need it actually. So let me be patient, I turn it on. Because I have a couple of figures that I want to show you. And okay. Not sure whether it works, we will see. Should work. Yeah, it's coming. And so, as I said, observation and observation monitoring, it's not, as I said, an easy task. And it's relatively easy when we talk about surface water resources. When we talk about groundwater resources, observing is a little bit more difficult. And the reason is that, of course, we are talking about something that we don't see, and therefore something that is more difficult to assess. And I want to say a few words, let me see if I can get it back, about groundwater resources. Yeah, it's back. So, okay, here you can see an example. Let me try to get it larger. Doesn't become larger in this case. Let me see. Okay, yeah, a little bit better. But I need to do this. So here is an example of a groundwater body, and let me see if I can turn the light off at least here, because so you can see. I want to just make clear how groundwater bodies look like, and this is an example of a groundwater body that is confined. So here you see some impermeable layer, another bottom layer that is supposed to be impermeable, so no porosity, no water that goes through. The brown part means that there is no flow of water in it. And you see we have some recharge. The yellow part is permeable medium, and therefore we can have infiltration here. When it rains, we have infiltration in the soil, and water goes down and goes into the groundwater body. And this groundwater body is in the lower part confined. It means that it's included between two impermeable layers. And being confined is under pressure, because water that is at a higher level here makes pressure on water on the lower level. You know probably, I don't know how to say this in English, the principle of the communicating, yeah, how do you say in English? Quasi comunicante, I don't know. But anyway, you know that when you have a body of water, you have, if the body of water is free, you have that the water surface is horizontal, meaning that the water surface is at the same level. In this case, the body is not free, it's confined, and it means that if you dig a well here, you have water coming up along the well at the same level of the upper level of water that you have in the body, because you have here water transmits the pressure, and therefore you have water that goes up at the same level than here, And in this case, where the well is interrupted before reaching the upper level of water, you have water sprinkling out. And this is a nice feature of this confined aquifer. They are also called artesian aquifers. When you dig a well in it, you have water coming out spontaneously. It may happen. And instead, when you have the upper part of the aquifer, like here, that is in direct contact through a porous media with the atmosphere, we call about a phreatic aquifer. So if we refer to this aquifer, aquifer is a synonym for groundwater body. If you refer to this confined aquifer, but we look here, here it assumes the behavior of a phreatic aquifer, because it means that water is in contact with the atmosphere. And keep in mind that here you need to dig a well in order to get the water, but water doesn't come to the surface spontaneously. If I make a well here, it's, you need to pump it. Instead, in this case, the aquifer is confined, you may have water coming out spontaneously. In this case, again, if the well is positioned here, then you have to take water by pumping. Of course, this aquifer is recharged, but you easily understand that the recharge is limited to the part of the aquifer that is in touch with the porous media. It may be very limited, and therefore recharge may take a lot of time, a long time. And therefore, if you take too much water from here, you can exhaust this groundwater body. So keep in mind the difference between confined and unconfined aquifers, and the synonyms are artesian and phreatic aquifer. Very good. And this is, how do we monitor it? It's clear from this picture. If you dig a well, it's clear to everybody what a well is. Okay? It's a pozzo in Italian. This is a well, this is a well. If you dig a well, you can see the level of water. And if you take water from this well, like this one, for instance, or from this one, you may see after a while that the level of water goes down. It means that you are exhausting, probably you are using water in an unsustainable way. But you have to distinguish between seasonal changes, seasonal variability, and interannual variability. So it's a bit complicated, but anyway, the way of monitoring is by reaching the aquifer with a well and see what happens. So, for instance, in this case, sometimes wells are just built to monitor, not to take water, just to monitor. Like in this case, let's suppose that you take water from here, but you want to monitor what's going on, and therefore you use this well here to monitor what's going on. Sometimes the wells are just meant to control, and in this case they can be very small, like this diameter, and they are just pipes that are put into the aquifer. Water is allowed to come up along the pipe, and they are used just to measure the level. And they are called, in Italian, piezometry. I think in English is piezometers, I think. Okay. This is how we monitor groundwater. Of course, in a well or in a piezometer, you can also take some chemical parameters or thermodynamical parameters like temperature, like concentration of isotopes, etc. Okay, and let's now talk about, oh sorry, one thing I want to say that is specified in my web pages. When you measure water level in a well, you identify your monitoring variable, which is water level in a well, and you measure it a long time, of course. What you obtain is water level as a function of time. This is defined when we talk about a sequence of observations along time. In technical terms, we call it a time series. So time series is a sequence of observations depending on time. Okay. So here the time series is water level in a given well or piezometer. Now, let's now refer to rivers. I said this is easier. Actually, there are some complications, but it's a bit easier. And let me first introduce some terminology, because I said let's refer to a river, but it's too generic. Usually when we take water from a river, we want to take water from a specific place. And therefore, we have a river flowing down, and we want to take water here. Now, you see that in order to identify the location, I drew a line that is almost perpendicular to the river line. Indeed, when we refer to a river location, we refer to what is called a river cross-section. Everything is explained in the web pages, so I see that you are taking notes. This is fine, but you find everything there. But please take notes, because if you take notes, you better remember. Okay, it depends on you, of course. But okay, river cross section. How do we obtain it? We have to cut the river with a plane in order to get a river cross section in the desired location, and this plane is perpendicular to the velocity vector of the river here. Keep in mind that the velocity vector of the river is tangent, more or less, is tangential